Hi, my name is Jungpil Lee, and I'm so glad to introduce this work at ICASSP this year. Let me start the presentation. So, the work is titled Disentangled Multidimensional Material Learning for Music Similarity. This work was conducted in collaboration with Nicholas Bryan, Justin Salomon, Jae Jin from Adobe Research, and my advisor Juan Nam. And this work was performed during an internship at Adobe Research. So, this is the outline. The content will consist of background, methodology, experiments, and demo examples. Let me start it from background. Here is the problem definition. Let's suppose you are a video music director who is working on television and film production, or even YouTube content creation. And the situation is that you want to put the right music to the video. The work process in this field is typically done by making rough cut film using thumb track. The term thumb track is an existing piece of music which is used during the film editing to serve as a guidance for the tempo, mood, or atmosphere the director is looking for in a scene. Let's see an example. This is a clip of a movie Inception, and the first music will be a thumb track borrowed from movie Star Wars that shows the style of music the director wants to use in the scene. And the second music will be a produced soundtrack that is actually used in the movie Inception, based on the style of the thumb track. So let's carefully listen to them. Now we have a thumb track, but directly using it for the video is usually not allowed because of the copyright issue. So we need to find alternative music, and there are three ways to find the music you want. One way is to search for music by title, artist, and album information. However, in most cases, it is difficult to remind of this information for alternative licensed music. Second way is to search by tag, description, and attribute. However, it is also hard for novice users to use terminologies to express users' desired musical feel. The last way is to search by example, and this is the case when we try to find similar music with a thumb track. So we will focus on search by example scenario from here. When we consider music replacement problem in search by example scenario, there is an important property that we should consider when designing a similarity space, which is a specificity concept of music similarity. For example, the notion of similarity is largely depends on the target applications. When we think about audio fingerprinting, the goal is to find the exact matching song. And version identification, like cover song identification, is a task that aims to find different versions of a same song. When we think about the specificity of notion of similarity, these tasks can be located in relatively high specificity area. On the other hand, category-based retrieval, such as matching tag-based audio retrieval using genre-like labels, is located in a low score area in specificity dimension. Now, let's think about our application again. The goal is to find similar music using thumb track, and we can think of this task as finding as much as similar song to the query audio, but not exact same song. For example, similar major-minor feeling over timbre, instruments, vocal characteristics, similar tempo, and arrangement. We can think of our target application is located in this area, which is going to be the notion of similarity we want to tackle in. And there is also another important concept in music similarity, which is multidimensional music similarity. In actuality, music is a multidimensional phenomenon, and consequently, there are various different dimensions along which songs can be compared. For example, genre, mood, instrument, and tempo. In other words, songs can be simultaneously similar along some dimensions, while different along others. So if we can take into account multidimensional music similarity, we can search for music through multiple dimensions, and this can enhance users' music search experience a lot. Therefore, the goal of this work is to construct a music similarity space that can contribute to both high and low specificity and also multidimensional characteristics. And here, most of the previous works only considered unidimensional similarity characteristics. Now let's move on to the methodology. So the goal is to build a music similarity space, especially Euclidean space, for best search in real-world application. To do so, dim metric learning with triplet loss is used as base structure. The right figure indicates simple triplet networks. The model takes anchor positive and negative samples as inputs and calculate distance between anchor positive and anchor negative, and the loss is a hinge loss between them. On the other hand, if the space can be constructed with multidimensional subspaces, we can search for music through multiple dimensions. To do so, we adopt conditional similarity networks, a technique that has been proposed for attribute-based image retrieval problem. In their work, they try to disentangle the embedding features using condition information. What condition means here is that multiple similarity notions are treated as a separate similarity notion. For example, this is a simple triplet network, and in this case, triplets are chosen based on certain similarity notion, and the disentanglement is conducted by applying masking function over embedding features by certain similarity notion. Accordingly, the loss function is updated to consider masking function. Therefore, we applied this technique to disentangle music similarity space for the first time. So if we use an instrument similarity, sub-embedding space that contributes to only instrument notion is activated. And if it is mood similarity, then mood subspace is only activated. And same for other similarity notions. Furthermore, we applied additional technique to consider both high and low specificity characteristics. Actually, triplets can be sampled based on any similarity notion. First, it can be sampled based on category information, such as music tags, and this represents relatively low position in specificity dimension of music similarity. On the other hand, we can use track information as another type of similarity notion. In this case, anchor and positive samples are chosen from the same track, and negative one is from another track. We can think this track information can be located in relatively high in specificity dimension, because the task is discriminating whether they are from same song or not. When we recap the goal, our goal is to bridge between this high and low specificity, so we can use both information together. To do so, we combined two triplet networks. From the left branch, we sampled triplets based on track information, and from the right branch, we sampled triplets based on category information. We can regard the track-based sampling as representing timbre-related similarity, and the category-based sampling as an overall similar fields. And we combine these two losses. Finally, we also apply the conditional similarity networks masking function to disentangle the embedding space for category-based similarity notions. Especially for conditioning, we use genre, mood, instruments, and tempo notions to tackle our target applications. Regarding the basic architecture, the basic architecture FX is chosen after running many experiments with different convolutional building blocks. And it turns out that the inception model is only showing meaningful performance increase. So the final architecture is like this. One convolution layer and 6 inception blocks, and one inception block consists of 2 inception modules, one for temporal dimension reduction and the other for feature map reduction. Finally, the network is fully convolutional, so the model can take into account any length of inputs. From here, it's experiments. To implement the system, we use million-song dataset and last.fm tag annotations that are linked together. The length of total audio is 2,000 hours, and we use top 45 tags that can be categorized into genre, mood, and instruments following previous rule. To have more rich notion of similarity, we extracted tempo from audio using pre-built algorithm using Python MedMonk library. For evaluation, we use a set of held-up triplets sampled from test set using multiple similarity notions, especially to determine whether human subjects concur with the quantitative evaluation. We randomly sampled 4,000 triplets from the test set and asked people to annotate which track sounded more similar to the anchor. Each triplet was annotated by 5 to 12 people, resulting in 39,440 human annotations. We then filtered out triplets where the agreement was below 0.9, resulting in 879 high agreement human annotated triplets. For reproducibility, we share our dataset of user similarity ratings, DIMSIM, online, along with audio similarity examples. And here's the results. More details can be found from the paper, but there are mainly two takeaways. First, disentangling multidimensional embedding space gives an opportunity to search through each multidimensional music similarity space. And also, it further improved general feature learning capacity. Second, adding track regularization helps in constructing specificity control, and the model with track regularization was favored by user annotated triplets. Now let's listen to some demo. Here we have 5 demos, and each demo plays 4 songs in a row. The first song is a query, and the following 3 songs are rank 1, rank 2, and rank 3 retrieved songs out of 28K test database. So let's listen to them. And this is the end of the presentation. The main contribution can be summarized into 2, which are multidimensional music search and user similarity rated triplets. Thank you for the listening.